Okay, so good afternoon, everyone. Last talk of the day, and then you can go for beers. So this is my colleague Ahmed. He's a PhD student from Italy, and I'm a software engineer at Cisco working in the segment routing architecture team. And today I'm here to talk about segment routing, which is something quite different from all the talks that we've been seeing today, because all of them were focusing on different platforms, and this one, what is focusing is on the actual protocols on the network, actually on SP networks. So what I'll try to do is give you a brief overview of segment routing, the deployment use cases, and then talk a bit about VPP, Linux, and SRv, which you will see later what it actually is. So what is segment routing? The idea behind segment routing is that we actually leverage the paradigm of source routing. So what does this mean? That instead of programming all the routers in the network, what we are actually doing is that on the head end, we are actually adding the list of segments that a packet has to traverse through the network. So what this means is that if I want to go from Madrid to Amsterdam via Brussels, what I just need to do is when my packet is out from Madrid, I just add one little segment that is saying Brussels and then Amsterdam, and the packet will follow the shortest path to Brussels, and then it will go to Amsterdam. That's simple. And this is actually really scalable, because what this means is that you can implement any traffic engineering policy that you want, and you can actually put this together with any NFV deployment that you want. And actually one of the main benefits is that we can have policies end-to-end. So starting from the data center and traversing the entire network through the metro and one. So we have two data plane instantiations. One of them is MPLS, and the other one is IPv6. So in MPLS, what we are just doing is one segment is one MPLS label, and that's it. The second instantiation is IPv6. So in IPv6, what we are doing is we are using an IPv6 routing extension header, which it was defined 15 years ago, and we have one segment is one IPv6 address, and that's it. So the one I'm going to focus here today is on SRv6. So it's the IPv6 instantiation of segment routing. So, well, IPv6 adoption is a reality. This is a no-brainer, I can skip it. But what is interesting about IPv6 is that it's providing us reachability. And this is changing the way that SPs are building their actual network, because before they would have their MPLS core network, then they would have the legacy data center, then would have the access network. And now with IPv6, what you get is reachability from one end to the other end. So what is the cool thing of what we are trying to achieve with SRv6? Well, what we want to do is, okay, let's use SRv6 for the underlay. IPv6 is giving us reachability. Now, you want to build given traffic engineering or faster route techniques. Well, what did you do? Would you use RSVP? Okay, I don't know if you know a bit about it, but it actually scales really, really bad. So let's use instead segment routing. But we can go even further, because what would you do if you want to build an overlay? What do you use? UDP and VXLAN? Okay, we are adding UDP and VXLAN, two additional protocols. I think from memory is 12 bytes of information just to convey a tenant ID. We believe this is stupid. We can include actually our overlay in the segment routing policy itself. And then we have NFV. What is people doing today for NFV? They're actually doing NSH. NSH is an additional protocol that has a state per every chain, and we actually believe that we can remove it. So we can also use SRv6 here. And so what is this concept of SRv6 network programming? So what we actually want to do is to have the network behaving as an actual computer. So our segments, which before I was saying that it was 128 bits, will be split in between locator and function. So the locator, it will be just a first part of the address, and it will give us routing up to a given device in the network. And then when we get to that device, what we are doing is we are executing that given function. And this function can be anything. It can be MPU related, so very related to the IP fabric, like do a cross connect, or that's it, so there's path up to X and then do cross connect. Or it can be something very intensive, like container, a VM, etc. And bear in mind that there is flexible bit selection. And actually, if you look at any programming language, well, you have the functions, but then of course you also have arguments. So these segments can also have an argument part of it. And all these, there is a flexible bit selection that you can put here. And so what we are doing is, well, we are actually, a network program is just going to be a list of segments, and what we are going to do is just go through the network, go first to locator 1, execute function 1. Then we are going to go to locator 2 and execute function 2, and then we are going to locator 3 and we are going to execute the function 3. So it's kind of simple and straightforward. So if we look at an IP packet, well, what we are seeing is that we would have our IPv6 header, and within this IPv6 header, we have an extension header that is going to be the segment routing header, and we are just going to have our list of segments. And we are just going to have the active segment copied into the actual destination address. And then we will have the IPv6 payload as it would be expected. So this segment routing header, what does it have? It has the actual list of segments, but then it also has some more things. It has global arguments. Let's say we want to give performance information, security, location information. So we have this metadata that we can add. Then we also have, on the other hand, we have a tag that is going to be used for group-based policies. And if you look, this very simple structure that is just a tag, the segment left pointing to the active segment, and this metadata is exactly what we have defined on the ITF. So it's very simple. So what is a segment routing? What is a seed? What is a segment? What is the function that we are executing? So the most easy and straightforward example, go through the ECMP hour shortest path up to a given node in the network. So let's say I'm on A1 and I want to go through the shortest path up to A4, and then I want to go through the shortest path up to A6. So then I just have to add into my packet a segment routing header with the segments A4, A6, and A8. And that's it. But let's say that now I want to cross this link over here that has an extremely high metric. So then what I do is, instead of the end function, I would just do the endpoint with cross-connect to neighbor function. So then what I have is that my first segment is going to be A4 concurrent C5, which is going to mean go to the node A4 and then do a cross-connect to the neighbor 5. And that's it. So what we are doing is really, from the source, we just add a list of segments, and the packet is going to follow that through the network. So I want to give you a brief overview of what are our deployment use cases. So we have a bunch of deployment use cases related with traffic engineering, and a lot of them have been deployed in SRMPLS. We have a lot of customers for SRMPLS that have deployed, and they're extremely happy. And the main deployment use cases, well, the first one is TLFA. So TLFA, what it is a fast route mechanism that in essence is really cool, because what it's doing is that the actual repair is following the post-convergence path. And it actually works in any topology. So actually TLFA stands for topology independent loop free alternates. So in essence, the way this works is that in case you have, for example, a flow from 1 to up to node 5, then there is this node 6 in between, and what he's going to know is, okay, so my primary path towards A5 is just going to be via this straight link, but in case there is a failure in this link, what I have to do is just insert the segment A2 colon C4. So then now let's say that there is a failure in the network in this link, and so what is actually going to happen is that A5 is just going to insert in all the traffic this segment A2 colon C4, that what it's going to do is it's going to route the traffic up to the node 2, and then it's going to do a cross-connect. And this fast route mechanism is active as long as the IGP hasn't reconverged. But you can see that once the IGP reconverges, the traffic will actually follow that path. So that's a really good use case. And then the other use case that all the service providers have deployed is, in essence, centralized DE. So you have an SDN controller that is computing, has visibility of all the network, and what it's going to do is that in case that I have an application on 12, and he says, okay, I want to go up to 7, give me a low latency path. So this SDN controller is going to compute a path, and it's just going to return the list of segments. And then 12 is just going to add that list of segments, and as simple as that, it can cross several different domains. And we can, well, we have all the input that is standard, things that are there, BGPLS telemetry, all the policies are PSET, BGPT, NetConv, and all the algorithms that are segment routing native algorithms that we actually developed. But all of this is completely standardized. But now with SRv6, we can do some things which are a bit more interesting. So we can do the overlays. So let's say that I have a green customer, and I want to build a green overlay. So what is going to happen is that 2 is going to advertise, okay, I have a neighbor V/64, and it's reachable via A2 colon C4. So now I'm on the node 1 and I receive traffic from my neighbor 3 that is destined towards this neighbor v/64. So what 1 is going to do is he's just going to encapsulate it and he's just going to add the segment that was advertised, A2 : C4, and the traffic will reach to 2 and then it will be decapsulated and sent towards 4. Now, but what I said at the beginning is that we cannot only do overlays, but we can do also overlays with underlay control. Because what we want to do is eliminate all the protocols from the network which are not necessary, like SRv6. So let's say that in this case, our neighbor 2 is just advertising the green tenant v/64 via A2 : C4, but with a given latency contract, an ESLA contract. So then in this case, what is going to happen is that the node 1 is going to encapsulate the packet and is going to add 2 segments. So the first segment is just going to be a segment to do traffic engineering in the network, so in order to achieve that low latency objective, and then I'm just going to have my cross-connect segment to reach my customer v/64. And in the same way, I can also have integrated NFV. And the good thing about segment routing is that, well, as opposed to NSH, we are not creating any per chain in the fabric. And we have actually developed some mechanisms such that the applications can be segment routing aware or not, and we can actually do IPv4, IPv6, and layer 2 traffic. So let's give the same example that we had before, but in this case we want to have a low latency and a SRv chain that is going through 2 appliances on the server 3 and server 5. So what is going to happen is that my node 1 is going to add simply 2 more segments into the segment routing header, and these 2 segments are going to be A3 : A32, which is just going to be an application, a container running in that server. Then I'm going to have a segment A4, which is just going to be for traffic engineering in the network. And then I'm just going to have another segment for going through another server, and then the final segment that is doing my decapsulation and cross-connect. And as simple as that, I can build my NFV all together integrated with the overlay and the underlay, and it's as simple as that. So, SRv chaining. Well, what I mentioned is there are 2 types of NFVs. We can actually have segment routing aware NFVs, and we can have segment routing unaware. So for the segment routing aware NFVs, what we have done is we have added support into the Linux kernel. So we have just added support in the Linux in order to create the smarter applications, and one of the examples is Sarah, that Ahmed is going to talk in 5 minutes about it. And then for the segment routing unaware BNFs, what we have done is we have leveraged VPP as a VM or container vSwitch to do this segment routing processing. So starting by VPP, well, I think we had plenty of introductions about VPP, but what I would like to mention is that we have developed our entire IETF draft on SRv6 on VPP, which is available, open source. And in the specific case of for doing SRv chaining, what we have done is we have developed 3 different segment routing functionalities, such that what we can do is, well, when I have traffic, for example, coming and I have VPP running and I have, for example, 2 BNFs running in containers, I actually remove here the segment routing header, I send it to my container, and then when the traffic is back, I add back the segment routing header with my list of segments. So that's pretty stupid, but it actually works with all the appliances that are not segment routing aware. And then on VPP, what we have actually done also in the context of BNFs and SRv chaining is we have done an SRv6 local seed development kit, that we call it, that in essence what we are giving you is a complete template, so that in case that you want to develop any SRv6 functionality, you only need to write a few lines of code. So we are giving you a VPP graph node, we are doing the segment routing header processing, and in essence what you need to do is just type into there the lines of code that you want to do into all of your packets. But you don't have to take care of anything, handling the FIB, all these things, you don't need to take care of it, we do it for you. So it's just really filling like very few lines of code, and I think literally there is 1 line saying insert code here. Like it's really, really simple. So then Linux.
So I'm gonna cover the implementation or the support of SRv6 in the Linux kernel. Okay, we agree that SRv6 is cool and we can use it in many stuff. So first, SRv6 was supported in Linux 4.10, which was released in February 2017. The first release or the first support in the Linux kernel supports the basic operation, which is end, which basically means read the segment routing header, update the destination address of the packet to be the next seed in the chain, and then forward the packet. Other behavior that were supported is the insert and the encap, where you want to take the IPv6 traffic and insert it into SRv6 policy, which you add an IPv6 header and segment routing header. This SRv6 behavior is supported on interface basis. So any IPv6 address that is associated with an interface in Linux, and this interface has the SRv6 enabled, so we consider it as local seed. Also, IP route 2 was extended to support adding an SRv6 policy, and here if you want to enable SRv6, you have to enable first the SRv6, and then per interface you can just like sysctl for per interface to enable the SRv6. And if you want to add the segment routing policy, what you have to do is it's implemented like as a lightweight tunnels in the Linux kernel. So basically you match on this prefix, this is your local seed, and here you choose the encapsulation mode, which is segment routing v6, and the mode of the encapsulation in segment routing v6, which can be insert or encapsulation, and you add the seed list that you want to encapsulate or you want to add on the top of the bucket. And then in kernel 4.14, which was released in last November, more support comes to the Linux kernel regarding SRv6, like the encap layer 2, which allow you to encapsulate layer 2 frames in segment routing encapsulation for the use cases of layer 2 VPN, and also it supports encapsulation of IPv4 traffic into SRv6, and some other functions that you can find more information in the segment routing IETF draft. Also, IP route again was extended to support the new feature. Here you can choose which function you want to you add your local seed and the action required for this local seed, and then the device or which is the routing table that is used as a local seed table. This what is in the Linux tree. There are some other implementations that is out of the tree. Basically, this one for supporting the chaining of SRv6 unaware function. So basically, you have a network service function that is running into a container, but this service function. This kernel module is inserted in the pre-routing hook, and it takes the packet, removes the SR encapsulation before handing the packet to the service function, and then cache the header. And when the packet comes back from the service function, we insert the segment routing information that we cached, and then the packet continue the traversal of the Linux kernel. So this was for the unaware service function, but then there are more advantage of having your service function or network function service routing aware. First is, if you have a service function that's segment routing unaware, you need to configure per VMF or per service function a state in your machine. But if you have your segment routing, if you have your service function segment routing aware, you don't need to have this state information. Basically, you can leverage all of the information in the segment routing header, and the service function has a complete vision of the path of the packet. So if you have a firewall, it has a complete vision of the path of the packet, so it can filter the packet. So what we implemented as a segment routing aware service function, what we call SRv6, which is a segment routing aware firewall. This is the first ever segment routing aware function. Basically what it is, it's an advanced firewall with extended matching capabilities that can match packets based on the outer header or the segment routing header or even the inner packet. And also it can perform some segment routing specific application, especially for the case of service function chaining, where you can do branching inside your chain. So let's take an example of firewall. This is a normal firewall. If the firewall receives a segment routing packet, it has no way to see the information of the segment routing information. So the firewall has a limited view of the packet. If I run this firewall with a proxy solution, so when it receives the SRv6 packet, it will remove the segment routing information, and basically the firewall can just see the inner packet. If I have a segment routing firewall, which is our implementation, when you receive the packet, the firewall can do matching based on all of this information, based on the outer header, the inner header, the segment routing information, the TLV, and also the payload of the packet. How we implemented our firewall, basically we extended the IP6 table implementation, the Linux kernel. We added 3 new extensions to the net filter framework, the segment routing header and the inner for matching the inner packet, and a new segment routing target for performing segment routing specific info action. And the first module is already now merged into the Linux tree. It should be available in Linux 4.16. And from the user space, we also extended the IP tables implementation to support these new functionalities. We add 3 shared libraries to IP table implementation, and also the one for already merged with IP tables 3. How the command line of the new firewall looks like. So basically, this is the SRh module, and this is the new matching option that you get. You can match basically on all of the fields of the segment routing header. You can match the inner source and destination of the packet, and also you can perform segment routing specific action, which means that, for example, if you receive a segment routing packet and this packet matches some criteria, you can say either go to the next, which is the default, go to the next seed in the seed list, or you can skip the next seed. For example, if you have a firewall followed by intrusion detection system and you want to skip the intrusion detection system for a subset of the traffic, you can say just skip the next seed and continue, or you can skip all of the seed list and go to the last one in the service chain. And here an example of extended rules that match based on the inner IP address of the packet and the segment routing header, and the action can be an standard action, which is drop, or it can also be an extended segment routing action, which go to the last service in the chain. And that's it. I believe to Pablo the conclusion.
Okay, so actually at the beginning, I was saying that IPv6 is providing usability. Well, what we actually believe is that SRv6 is actually unleashing the full IPv6 potential, because we can actually do, on top of IPv6, traffic engineering, fast route VPNs, and FB, things like, for example, network slicing for 5G, and SD1, for example, and all these with great scalability, with a huge amount of automation, and all together in a single protocol. And also, I would like to give you a brief overview of the SRv6 project, aside for SRMPLS, which started 4 years ago. So for SRv6, we actually did the very first demo for Comcast was actually in April 2016. But when we pushed really strong, it was on March 2017, last year, where we published the ATF draft, and we actually showed in MPLS World Congress with the VPP and the Linux implementations. And then from there, we added some Cisco implementations on Cisco hardware, some barefoot implementations, and then interrupts. And then late last year, we covered SD1 in the SD1 Summit, and then this year, what I can advance is that we are focusing a lot on 5G and network slicing. And just final slide, what I would like is, if you have time, just check our website, maybe try to read the draft, play with VPP and SRx, and really create your own segment routing our applications. It's extremely simple. We are saying that there is a huge market for it from the service provider markets, and in case you have any question, you can always write us, and we'll be glad to support you. So that's it. Now you can go for beers.
So anybody have any questions? We've got a few minutes.
How do you think segment routing will be compatible with all the offload technologies from the NIC, like the TCP offload, UDP offload, checksum offload, and so on?
I'm not sure I understood the question.
So I think the question was whether segment routing is compatible with all the offloading capabilities of the NIC. Yes, it is, but I mean, where do you want the compatibility? I mean, usually, the question why I say this is, well, usually you would have a TCP, you would have an end customer that is adding the TCP packet, and then it just reaches the SP network, and from there you add encapsulation. So where do you want to have the offload compatibility? Okay, yeah, so for example, in VPP, that is the example that we are, where's our expertise, it is compatible with the offloading capabilities where we do the proxy mechanisms. Then in other platforms, I would need to check. I don't know, but I don't see any reason why it would not be compatible. For example, how you compute a TCP checksum when you have a segment routing header is defined like 15 years ago in the RFC 2460. So there is nothing really to add compatibility for SRv6.
Any other questions? I will come around with the mic. Anybody up the back, down the sides, left side, right side? Is that the right or the left? No? In that case, thank you. I didn't get your name. Ahmed and Pedro. And that is the end of our SDN and NFV dev room for at least for another couple of hours. You're all invited to the Mannequin Piss Cafe at 7:30 p.m. There will be a round of drinks sponsored by Red Hat and a round of drinks sponsored by Cisco, DevNet. So you're welcome to join us. And we're looking forward to seeing you all next year if we manage to get this dev room again. I think this has been a great day. Thank you very much to my co-organizers. I got to call out Thomas Monjalon, Charles Echo, Roy Kinsella, and hiding over there, Chris Price. The five of us have been involved to the extent that people could for putting this together for the last few months. So thank you all. And thanks for coming.